Today is August 18th. In this session, we are going to do two things. First, I would like to go on with the material. I don't know if that's going to be enough, but hopefully, yes. I still have one more week, so we're fine. We're fine with the timing. And in the second part, I would like you to start preparing the report. So we're going to, I'm going to give some general, very specific instructions, and then we're going to go in groups, okay? So I'm going to ask Giovanna to set up just to break up in rooms, okay? From group 1, from room 1 through 8. And everybody knows its group numbers. So when we come back in the second part, each person will go to the corresponding group and we'll start working, okay? And then at the end, we will get together and see how far we have gone. After that, I hope that you really you are able to complete the rest of the assignment, okay? So that's the idea. Okay, so here. Can you see my PowerPoint presentation? Full screen, Giovanna?
Yes.
Okay, so this is what we reviewed in the last session. Okay, we considered that spectral density, okay, is the result of the combination of many components, okay? So we can think that this is split in little strips, okay? And each strip, okay, this area, okay, is the contribution from one harmonic, okay? So this area represents the contribution for each one of the harmonics. At the end, we have many harmonics we can combine, and this is what we are, this is the way we can do simulations, okay? So we need the area of each one of these strips, okay? So if the strip is not that small, okay, in that case, we can do something like this in this example, which is basically an integration using Simpson rule. Okay, so we go from very close to 0 until 0.25 radians per second. And then we go from 0.25 to 0.5 and so on. So to integrate, okay, in this area, we use this a Simpson rule. So we integrate the area and then we calculate this amplitude with the area multiplied by 2 and taking the square root. And that's this result here. So we see that the contribution from this strip is very small. It's 0 up to the third decimal. Then in the next interval, from 0.25 to 0.5, then we will have a measurable amplitude for the harmonic. So the harmonic will have this frequency, which is basically the frequency in the center of this strip, okay? And this is going to be the corresponding amplitude. Okay, we can repeat this, and this is a summary of that, okay? We have the central frequency of each range. This is the amplitude. This number is this one here. This number is that one there. And then here, what I do is I generate a random value for the phase shift between each harmonic. So basically, this thing here changes every time I do this calculation in Excel. So it's very nice because that reminds you that these things are randomic in essence. That means that every time you have different responses. Statistically, they correspond, but in the time domain, they are different, as it should be, because they are random processes, okay? we said a couple of words about the number of components that you need to do this breaking, this decomposition. And I mentioned the number that I received. I heard from professor, I don't remember the name. He's also a leader in this area, University of Trieste. And he uses 1,000 components. So these strips are very thin, okay? And in that case, you don't need to integrate because it's so thin. So what you do is you simply consider that each one of these could be approximated by a rectangle. So the area is just the height times the width. And that's it. So you don't need to do this integration. So you evaluate at the central point, divide by the width, and that's what you have. But that's something that we should have in our mind, because that's something that we could use. Okay, so we generate a time series, and with that, this time series, we could develop any statistics analysis. Okay. Yesterday, remember, Professor Trosh, he mentioned that there was a number about 900 and something outs. It looks like this number is very important. It looks like it gives me an idea of the number of hours that a specific type of ship is going to be active in during his entire life. You cannot expect, for example, a warship to be navigating all the time. Most of the time they are sitting on the dock, on the port, and then they navigate, but they navigate only a few hours. And then you accumulate all of those in lifetime, and that's the number that he mentioned. But in order to generate these things, you can do this. So for example, in this case, I'm using this as to generate the elevation of the sea surface. But we could do this, for example, for the bending moment, right? So we could generate the spectral density of the bending moment of the midship section. And from that point, we could do this and generate the variation that we could expect for the bending moment in a typical sea state. And we could try to observe maximum values, minimum values, and things like that. Remember that he mentioned last night that one of the problems is that if you do this for a longer period of time, okay, it is quite possible the larger value will increase and increase and increase. And the maximum value, statistically, you have to consider the length of time that you are going to be doing this analysis. So that's something that we can do using this decomposition. Now, let's go on. Let's go on. Now, after we have calculated the response spectrum or spectral density, okay, there are certain information that we can obtain from this distribution. Look, please look at the title. It doesn't say the spectral density or the spectrum of the sea surface elevation. Okay, we're assuming that we have calculated the response spectrum. Let me remind here the equation that we deduced for that. Okay, we have the spectral density of the wave elevation of free surface elevation multiplied by the rho. Oh man, Jesus Christ. Please don't write on my screen. Okay, multiply by the rho squared. Remember, rho in general is a complex quantity. So we need to take the amplitude in the square. And the result is the spectral density of the response. Okay? So this is what we're talking about. We're talking about the spectrum of the response. Now, the response, for example, in the case that we're analyzing, okay, is the roll response of the ship, of the model. But this response could be the parameters that you want to analyze: bending moment, acceleration, or the propeller race. I mean, well, it can come out of the water. I think. Okay. Now let's suppose that we have it. Let's suppose that we have it. Now we have one problem. Then the problem, before going into these moments, is that let me draw here just a little picture. Okay. Let's suppose I have, this is the ship. And the problem is that we assume that the ship receives waves from this direction. But it's not completely true, right? Professor Trosh last night showed some videos, and you could see that the waves did not come from one single direction. It was mostly from one direction. But in general, you could see that there was some waves coming in one direction, but there was some others coming from a different direction. So what we can expect is that we could have waves coming from this direction, but also some waves coming from another direction. For example, okay? And in general, there could be a continuous distribution. So the ship moves in one direction, but receives the waves from many directions, okay? So in order to do that, to consider that in our analysis, what we have to do is we have to consider that the spectral density of the incoming waves, okay, it's composed or includes the direction of the incoming waves. And this is this, okay? So as a result of this, we have to say that the spectral density of the incoming waves depends not only on the frequency, which depends on the wavelength, but also depends on the direction with respect to the motion of the ship, okay? Now, this function, okay, depends on two variables, right? It's very difficult to set up. So what people do is this. We assume that we can develop this function using Pearson-Moskowitz, ITTC, or something like that. And then we assume that there is one main direction from which we receive the waves. But as we can probably see in real life, we cannot consider that all the waves are coming from one single direction, okay? But they are spread. And this function, m as function of beta, is that function that includes the spreading, these different directions that you receive the waves in a ship, okay? So let's suppose I'm moving in this direction, I'm receiving the waves in that direction, but that's the main direction. And from that point, you can assume that you're going to receive some waves in that direction, but they are less likely. Similarly, in the other direction. Okay, mostly they are coming in this direction, mostly. But there are some that comes in this direction and in this direction. So adding all of that, you're going to have a certain energy in the C state. Okay, now, how do we set up this function m sub beta? Okay, there are several models, okay? And one of the most common that we can apply is the cosine squared. Okay, so what we are saying is that, okay, let me try to draw something like this, okay? Okay, so we are considering that this is the ship. And let's suppose that we receive waves mainly from this direction. But, okay, we also receive waves in this direction. And this angle is beta. But these waves are multiplied by this parameter because you have to have in mind that these waves from the, in this case, from the fore end, are the most, is the direction from where the most of the waves are coming. Okay, and then in this other direction, yes, there are some waves here, but in this direction, the waves has less smaller amplitude. Okay, so mostly from here, less from here, and even less from this direction. But in general, you see waves from all directions, right? And if you add the energy from all of these, we should have the energy of the sea state that you are analyzing, okay? And this function has this property, okay? So you multiply that by this one here and integrate in every direction. And at the end, you're going to have the original energy that you had here. Remember that 2 divided by pi is less than 1, okay? So when beta is 0, that's the main direction, that this is 1. But this multiplied by 2 divided by pi, so this factor is less than 1. And from that point, cosine squared reduces. So when you change the direction, yeah, you have some energy in the waves coming from this direction, but the energy is smaller than the waves that are coming in the main direction of the sea state. People, are you following my explanation? Okay, and this is what we call the cosine squared spreading. Okay, so probably you will need to include that in your calculations in the in MaxSurf. Okay, now this is an evaluation of this cosine squared function, and let me read this. Okay, so if we take one direction, okay, in direction, we see that we have most of the energy coming in the waves coming in this direction. In the other direction, they are reduced. And eventually, in this direction, basically, there's no energy. So basically, it's mostly from here, waves smaller, 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 smaller. And basically, in this direction, basically, you do not receive waves. Okay, in the other direction because it's symmetric. Okay, that's the idea behind this table. Okay, here we have something very interesting. Okay, on the right, okay, this is the function or the spectral density considering simultaneously the wavelength or the wave frequency and the direction. So you see that this has some funny shape here and all of that. And here, they model this with the product of the like that. And this is the cosine square model. And you see that this looks very similar to this one here, meaning that this is the real one. The right-hand side is the real. So you took measurements, right, in a certain area. So you could develop this spectral density considering the position. So you're receiving waves in different directions, right? And then on the left-hand side, you see that this is the result of applying the spreading, cosine square spreading. And it looks very similar. So this is a measure that this formulation is really valid, and we use it very commonly. Okay, so that makes more realistic analysis, since you can imagine that when you navigate, you do not receive from a single direction all the waves. There are some spread, and this function cosine squared is a good measure of that spread. Okay, now we have all of that in our mind, and we can say, okay, let's calculate now what we call the short crested. Okay, short crested. What do we mean by that? With short crested, we mean that since short crested, that means that the wavelength is kind of short. That means that you receive waves from different directions. Okay. On the contrary, if you talk about a long crested sea, that means that the waves are very long. So basically, you can assume that all the waves coming from one single direction. okay? It is possible that in some calculations, you need to consider long-crested seas, okay? But in general, we tend to calculate with considering short-crested seas. That means that we expect to have a variation of the direction from where the waves are coming, okay? So, and you see here that when you consider long-crested, basically, you do not consider that there is some spread. You simply said, okay, the waves are coming only from this direction and that's it. Now, could be that in certain extreme situation that can happen closely, but it's just an extreme. In general, we receive waves from every direction. Okay, so that's something that we have to have in our mind. Okay. If you analyze with the short-crested sea, in that case, you have to include here this beta, and you have to remember that if you receive waves in the different direction, the response of the ship, that is the row, changes in direction. In this case, okay, you said, okay, I'm going to receive waves from this direction. And in that direction, you have to calculate the row. But since you have only one single direction, all this energy is just in one single direction. But in this case, this is spread. Okay, so when you have short-crested sea, basically you cannot avoid having basically the 6 motions. In long-crested seas, for example, you receive long-crested seas from the bow. Basically, you expect to have heave and pitch, unless there is some parametric resonance, which is a more complex situation. Now, let's suppose that we have calculated the response spectrum. Okay? You have decided, or the ship owner has told you that you have to do this analysis using short-crested or long-crested seas. Okay, you have calculated the spectral density of the response. What do we do now? Okay, there are certain parameters that can be calculated, and these are what we call the moments of the spectral density. Okay, how do we calculate that? Okay, we calculate basically in a similar way. Okay, remember when we had a weight distribution, you could calculate the first moment to determine the LCG. You could calculate the second moment, okay, x squared dw. And you could calculate in this way the second moment of inertia. Similarly with this case. Okay, so you take the frequency omega, raise it to the certain power, multiplied by the area below the spectral density. Now, you have to remember that when you integrate this, okay, you can change this exponent. And according to the exponent, you give the name to the resulting moment. Okay, so if you set n equal to 0, so this is 1, basically you calculate the area below the curve. So M0 is basically the area below the curve of the spectral density. How do you call the area below the spectral density, Mr. Matute? Do you remember how do you call the area below the spectral density, Mr. Matute? The area below the spectral density. Pardon me? Didn't get it?
Rm squared.
Pardon me?
He say rod meter squared.
Square. Yeah, you're right. You're right. So if you calculate M0, that's root mean squared. But then you can calculate another moments. For example, the next one is M2. So what you do is you take n equal to 2 here. And of course, this function here, you do not know the explicit formulation for S. What you know is a group of values for the spectral density. So what you have to do is you have to develop this integration numerically. And these are the most common, 0, 2, and 4. So you can calculate M0, M2, and 4 of the spectral density distributions, okay? And remember, we have to be careful with the units, okay? So in general, the spectral density, for example, of the roll would be degrees squared times second. Okay, so when you multiply by frequency, that's 1/2, the result is going to be degrees squared. If you multiply this by 1/2 squared and integrate, the result is going to be degrees squared, second squared, etc. So we have to be careful with that. Okay? Okay, so the number is for short crested seas, considering this spreading. In the most common formulation to include this spreading is the cosine squared, or this is for long crested sea when you basically assume that mostly the waves are coming from one single direction. Okay, now let's suppose that we have done this integration and we have calculated these moments, M0, M2, and 4. What do we do next? Well, we already answered that question. And also the units. Okay, now in this case, this is an example that this is a thesis from engineer Priscila Salazar. We did these calculations in this year. So in this case, this is a spectral density considering different directions. Okay, and you can see that the highest value occurs when you receive wave from the bow. Makes sense, right? Because in that case, the heave and pitch are going to be very large. Okay, when you receive waves from the side here, okay, basically the bending moment doesn't change much. So this is very small. Okay, and that we could integrate and calculate all of these moments. This is what I'm showing here. Okay, so we can calculate M0, M2, and 4. And these are parameters that I'll mention that in a second. Okay, but as I said before, you do not know the function. You know values of the function. So the only way you have to integrate is numerical integration. Okay, for example, in this case, I'm using just the very well-known Simpson first rule, and that's it. Okay. Now, after we have calculated these moments, what can we do? Well, there are several things that we can do. For example, if we know the M4 and M2 moments, we could calculate in this way, and that represents the average period between peaks or crests. Let me remind you. We have something like this. We go like this. So we have a peak here and another peak here. So this is the period of the crest 1. Here to here. That's the period crest 2. This is the third, and this is the fourth. And from here, we can take an average of that. Okay, this average can be proven. I am not going to do it here. Has this frequency. So with this frequency, we can set this equal to 2 pi divided by tau sub c average, which is this one here. What for do we need this? Remember that, for example, let's suppose that the response right now is the relative motion between the sea surface and the deck motion. If this amplitude of this relative motion is higher than the free board, that means that the water has come on the deck. So you have water on the deck. Now, sub c is the average of the period between the fact that you are having water on the deck. If this period is very small, you are in trouble, because that means that you are receiving water on the deck. And it is likely that there is not enough time so the water can come down before you receive more water. So probably it's possible that the water will accumulate on the deck, and we have to be careful with that. Yeah. So that's the usefulness of this parameter. Okay. Now, well, I just wrote it here. Okay. Now, what can we do with that? Well, this is what we can do. Let's suppose that we know we have calculated this average period. Okay. So it's 2 pi divided omega c. So that's this number of seconds after which you have a new crest, right? So if you divide 60 seconds that you have in 1 minute by this period, which are cycles for a crest, this quotient, 30 omega c over pi, corresponds to the number of maxima that you're going to have in 1 minute. Instead of 60, for example, you could calculate in 1 hour. So instead of 60, you multiply this by 3,600 seconds, which have in one hour. And in that case, okay, you're going to have 1,800 times omega c divided by pi, and that's going to be the number of crests that you're going to have in 1 hour. Okay, so that's a good number. Now, we're interested, okay, in how many of those maxima makes me have water on the deck. So what I'm going to do is I'm going to evaluate the probability that this motion, which is a random motion, has a higher a value, which is higher than the freeboard. And I can evaluate that using the Rayleigh distribution. So what we can do is this. We can assume that these crests follow the Rayleigh distribution. So this is going to be the probability that Z sub D is being exceeded. If I multiply this probability times the number of crests that I'm going to have in 1 minute, this product will give me the number of maxima, okay, in 1 minute that have exceeded Z sub D. Okay, for example, let's suppose that number is 20. That means that in 1 minute, in 20 occasions, you are going to have water on the deck, water on the deck, water on the deck. That's too often. What do you have to do? Well, in that case, what I can do is I can increase the freeboard. If I increase Z sub D, this probability will be lower. So instead of 30, you're going to have 1 or 2 times in a minute that you're going to have water on the deck. So you receive water on the deck, the water flows down, the deck gets dry again, and until the next time you receive more water. But no water, basically, it's going to accumulate. So you are safe. Okay? Now, the problem that you ask yourself is, okay, and how do I know if the number of times that this happens in 1 minute, it's good or it's bad, it's too often? That's when the table that I showed you last class comes into play, right? Because there's people who accumulates a lot of information and produces these recommended values. Or it is possible, for example, that you can look it up in other literature. For example, the classification rules from societies. And since we assume that the Rayleigh distribution is a good approximation of the maxima, instead of P of Z, we could recall and replace it by the Rayleigh probability distribution that we know. Okay, it's quite useful, and all of that starts with the knowledge of the moments M2 and M4. So M2 M4 divided by M2 and square root of that give you the average frequency between crests. Average. Remember, this is a random process, so don't expect to have the distance between crests to be constant. No, that changes in time. But the average is that. Okay, similarly, people, you have to be careful. This is omega sub c, okay? Now, we could find something similar for the average of the up crossing. So remember, we have here like that. So here, I have an up crossing, okay? Here, I have the next up crossing. Here, next up crossing, and here, next up crossing. So this is the period. This is the period. This is the period. And from here, we could calculate the average. And this pi divided this average. And we can calculate using this M2 and M0. When we go in extreme, okay, and the two are the same, in that case, that means that basically you have a harmonic motion. In a harmonic motion, the distance between crests is the same distance between upcrossing. So that's an extreme case. In general, we don't have that, okay? So it's going to be some difference, but we could calculate both with M0, M2, and M4. So when you talk about average period, you have to be careful. Is this just average period, or this average period between crests, between zero upcrossing, or what? Okay, so similarly with the height, is this average height? Is significant height, or is the average or 1/10 of the highest? So it's difficult, different meaning. So we have to be careful when we specify that. Okay, now, this is something that we mentioned here, right? For example, you see that here, maximum, which is below the zero. That means that this is negative. So it's kind of weird, right? Okay. If we have many of these, or for example here, I have a minimum, but it's positive. It's a minimum, which is positive. Kind of weird. Because if we talk about, if we mention that we are considering a minimum, we expect to be negative. If we consider a maximum, we expect it to be positive. So this parameter here, epsilon, helps us to evaluate if there are many of these positive negatives or negative minima. Okay? And this parameter is calculated in this way. And what do we mean by this? Okay, if we have a spectral density like this, see that all the energy is located in a very narrow band of frequency. So this is what we call a narrow banded process. On the contrary, if we have something like this is not narrow banded. This is wide banded. Okay. Now, if you have wide banded process, in that case, you could expect that many of these maxima could be negative, or many of these minimum could be positive. This makes statistically make you give you a hard time trying to make any conclusion. okay? And to judge if you are close to narrow banded or wide banded is this parameter epsilon. And you can calculate it using this formula, which depends on the moments, okay? Probably you're going to ask me, what's the range? Well, that depends on the phenomena. I'm not going to give you any. There are certain ranges, but that depends on the type of parameter. Okay, so you can calculate it, and you can look in references and see if this or that parameter is if this value epsilon is between here and here, you can consider it as narrow banded or not. If the phenomena is narrow banded, that means that the Raleigh is a good approximation for the maxima. Last night, remember, Professor Throsh mentioned that he uses Weibull. The Weibull function is another distribution. Depends on certain parameters. If you set these parameters with a certain values, you recuperate the Raleigh distribution. But Raleigh is more restricted, but it assumes that the phenomena is narrow banded. But for that, you need epsilon to be in a certain range, okay? So when epsilon gets close to 0, that means that the phenomena could be considered as narrow banded. But how close to 0? That depends on the parameter. I'm not going to give you any. The other end, if you get a very high epsilon, close to 1, that means that you are very wide banded. So you could expect many maxima, which are negative, or many minimum, which are positive. It's kind of weird. Yeah, that's because you got frequencies all over the place. Then this narrow, wide presence of many frequencies give you this type of things, right? Maxima, which are negative, minima, which are positive. Okay, and this epsilon, which is calculated using these moments, it can be used for that. Okay, and we go on with this this table. Hopefully now makes a little bit more of sense than before. And here, okay, you can see that if you can calculate the spectral density, then you can calculate the area. And from that, you get the square root, and you can calculate the RMS. You can use these values as reference. If your ship is having an RMS very high, higher than this, that means that probably you need to do something in that respect. Okay, and that depends on the type of function that the ship is doing, and if it is a naval or a commercial hull. Remember that this is this was a collection of information gathered in 1988. So probably by now you could find more up-to-date information, okay, which are more precise probably. People, is there any questions about this? Any questions so far? We're going to go to a break, and when we return, a 5-minute break, when we return, I'm going to give you a short explanation of some details of the calculation. Then we're going to go to break up in rooms. Each group will, each student knows the number of this group, so you can move, you can go to your group, and you can start working on that, okay? I'm going to pass by each one of the groups to see if there's any problem, and then at the end, I will ask you to come back, and for the last 5 minutes, we'll see if we can share some information so we can see that we're going in the correct direction, okay? So, Giovanna, would you please stop the recording? 5 minutes.